the previous video explained how you start with the pre-variety and get from it a scheme. So if you start with X, how you get X scheme. And the big question for the rest of the chapter is, now the converse question, given any scheme Y, when is this of the form Y equals X scheme for X a pre-variety over this algebraically closed field K? So can you recognize what you get, which part of this whole theory of schemes you got? And some ideas about this. So the pre-varieties that we started with, they are glued together, as we recalled, from finitely many affine varieties. And this aspect we haven't seen for the schemes. They can be glued together from arbitrarily many affine schemes. Then, even on the level of affine varieties, we knew that the coordinate ring is always a finitely generated K algebra, and it's also reduced. So all of these properties here, we would somehow need to impose on the scheme level. This was on the level of the individual objects, and then also for the morphisms. So sorry, I guess this should just be the morphisms between affine varieties correspond to morphisms of their coordinate rings, which are K algebra homomorphisms. This is another thing in general we could allow on the level of affine schemes. We allow arbitrary ring homomorphisms. So we need to somehow impose that these ring homomorphisms should be between K algebras. And then the final thing, which will also be the final kind of video, is that when X is a variety, then we have imposed this condition that X is separated. So in other words, that diagonal inside X cross X is closed. And here, if we wanted to lift this to the level of schemes, we would need to define, well, given X a scheme, what is X cross X as a scheme? What is the diagonal? And then we already know basically what it means for this to be closed. So, so here, this was kind of just an overview of what is about to come to motivate it a bit. But then now come the kind of the rigorous definitions, making all of this precise. So what properties of schemes we can impose. So the idea is, motivated by this list here, we will now define some properties which make sense for arbitrary schemes. And then we're going to recognize that pre-varieties are exactly schemes having this list of properties, and varieties are these schemes which have one additional property, this property of being separated. So that's the preview, and now come the rigorous definitions. So some properties of schemes. If Y is a scheme, then a scheme over Y is a pair X, F, where X is a scheme and F is a morphism from X to Y. And often in the notation, you also write X really over Y, so somehow it's higher than Y. And so somehow a priori a scheme over Y is just the data of this morphism. And then if you have two such things, so X1 sitting over Y and X2 also sitting over the same Y, then a morphism between them as schemes over Y is a morphism filling in this diagram here, such that it commutes. So in other words, you don't allow arbitrary morphisms from X1 to X2, but they must commute with these maps to Y. And so if Y is of the form spec S or S ring, then you often just say X is a scheme over S. And that just means scheme over spec S. And then if also this here is affine, if this is spec R, then we have seen a map from spec R to spec S is equivalent to a map from S to R, a ring homomorphism. So this is the first property, being a scheme And in a certain sense, this is not a property of this abstract scheme X, but it's kind of additional data that we impose. So the next thing is that when we have such a scheme over Y, then we say this is of finite type. And you can also just say, well, given the morphism of schemes, it is of finite type. If so now come the finiteness assumptions, and they come in two ways. So first of all, so everything needs to boil down to some commutative algebra. So we first say that there is an open cover of the target. So this is in red here, an open cover by affine schemes. So do we have these UI, which are spec of Si? And then you get a pre-image, right? So this is then an open subset of X. And then we want to have a finite open cover of this pre-image here. So this is in blue. So these finitely many pieces, which are also affine varieties. So they give us these rings Rij. And then the fact that the spec Rij maps to spec Si means, by what we just recalled, that we get ring homomorphisms from Si to Rij. We get ring homomorphism from here to there, which is basically like pulling back functions. If you have a function here, you can pull it back, you get a function here. And this ring homomorphism should make Rij a finitely generated Si algebra. There's kind of two finiteness here. First of all, the cover has finitely many elements, and then this ring homomorphism makes this thing a finitely generated algebra over the base. So you already see this will explain this first finiteness, having finitely many elements of the cover. This somewhat corresponds to that pre-varieties have a cover by finitely many affine varieties. And then the second one corresponds to the fact that these are finitely generated algebras over K. And then we see the last property that we're going to look at is now this reducedness. And that is actually very easy. You just say a scheme X is reduced if all of these rings, right, it's a ring space. So for any U inside X open, you get this ring OXU. And we just want that these rings are reduced. So in other words, they have no non-zero nilpotent elements. So that was charmingly simple. We just asked that there's no nilpotent functions except for 0 on any open subset of X. So these were the three properties which we're going to see will allow us to characterize these pre-varieties. And if you do, if you go deeper into scheme theory than we are going to do it, then you would find, schemes, there's lots of properties, lists of properties of these things. We're going to see now a small exercise which showcases something which you find more general, namely this last thing. So somehow for this property of being reduced, we gave a definition saying all of these rings are reduced rings. But in fact, there's equivalent characterizations. So when X is a scheme, the following three are equivalent. So X is reduced. So for all U inside X open, this is a reduced ring. Then the second one is something which you can actually check when on any cover you want. So you can say there exists an open cover by affine schemes such that the corresponding rings are reduced. And the third one is that something which you can check locally at the stalks, namely that for any point P in X, this local ring, OXP, is a reduced ring. So for many properties, there's these kind of equivalences saying something holds for any open, something holds for any open in a given cover, and something holds at the level of local rings. And so it's a nice exercise to see for this property here that these are all equivalent. And then once you have this, it gives you a lot of flexibility how you want to check reducedness. Maybe you have good information on the stalks. Maybe you have a very nice cover which explains it for you. And having this flexibility helps with proving things. Okay, so this was this exercise, and then making this final connection to the language of pre-varieties. Well, what does it mean? We have this general definition, what it means for X to be a scheme over Y for an arbitrary scheme Y. And when we take a very simple scheme, namely for K any field, what it means to be a scheme over this spec K, so scheme over K. Well, on the level of topological spaces, this is all very trivial. There's no information there, because as we said, a field has only a single prime ideal, namely the zero ideal. And so spec K is just a single point set, and there's exactly one map from any topological space to a single point set. So this thing doesn't contain any information. The information is hiding on the second data point, namely these pullback maps, right? Because for any U inside X open, you get this pullback map from K to OXU, at least if U is non-empty. And this map here, so somehow this goes from here to there, this pullback, so it's a ring homomorphism from K to this. And of course, this is just the definition of making this ring here into a K algebra. Here we now see the K algebra property that characterizes these pre-varieties. In particular, for any affine subset U equals spec R inside X, if X is a scheme over K, then R will automatically be a K algebra. And in a certain sense, being a scheme over K just means that all of these rings which help you cover X, they are K algebras, and they're kind of K algebras in a compatible way. If you have two of them overlapping, then how you identify these elements of K as functions is compatible on this overlap. Okay. And so collecting now all of these ideas, if X is not just any scheme over spec K, but if X is actually finite type over K, then this tells you that, well, this thing here has only a single possible affine cover, namely you need to take the full spec K. And then if you look at this property of being finite type over this means that you need to have a finite cover of the preimage, in other words, of all of X. So X has a finite cover by these affine things, and each of the affine each of the affine schemes comes from ring Ri, which by this property here is a K algebra. And then the finite type assumption tells you that this is a finitely generated K algebra. And now we're getting pretty close. So somehow, if you then also ask that X is reduced, then any of these things must be reduced. And then we have basically collected all of the properties that we need to characterize pre-varieties. And this is then formally stated here. So let's say Y is a scheme and K equals K bar is a field. Then we have that Y is equal to X scheme for X a pre-variety over K, if and only if Y is reduced and it has a map to spec K such that this map makes it finite type over K. So being a pre-variety just means basically having these three properties that we defined before. And moreover, the morphisms from X scheme to Y scheme as schemes over K, when X and Y are of this form, are exactly equivalent to the morphism of the corresponding pre-varieties. and this bijection takes this morphism and sends it to this F scheme that we had constructed in the last video. Okay, so this gives us a unique identification of the pre-varieties inside the schemes. And so let me again just give kind of the proof idea. So let's say we have this Y having all of these properties here. So basically show how to go from here to there. That's the interesting direction. So then so somehow if the interesting direction is you assume all of these properties, and then you need to come up with this pre-variety X such that Y equals to X scheme, right? So what we do is we first observe that we find this cover here that we discussed here, right? Because I mean we already did kind of half of the proof before. So if X is finite type over K, we have this covered by the Ri, and they are reduced finitely generated K algebras. So if we take this finite cover, then each of the Ri is finitely generated reduced K algebra. And then we have seen these are exactly all of the rings which can appear as the coordinate rings of an affine variety. So this is an old result. This is from the first part of the lecture, where we saw that this equivalence of categories between affine varieties over K and finitely generated reduced K algebras. And so somehow this gives us this collection Xi of affine varieties. And moreover, by the construction that we saw in the previous video, these UIs, these schemes which cover these schemes which cover Y are exactly the scheme version of these affine varieties which we got. And now we're already in pretty good shape because now we have these individual pieces which are affine varieties. They go to the right pieces covering Y, and then we'll just verify that these Xi clue together to a pre-variety X, because the UIs glue together to Y, and then using the same gluing maps, the Xi glue together to some pre-variety X, and the X scheme is equal to Y. So this is kind of the proof idea for this direction. And the other direction is in a certain sense a bit boring, because, I mean, if you have this property here, then cover X, this pre-varieties by affine varieties, and then you just check that all of these properties here are satisfied. That's how we motivated their definition. So this works pretty well. And then the final thing we want to show is that this equivalence between the morphisms. And for this, I mean, we have a well-defined map from here to there. And I mean, one thing that you should convince yourself of is that this, when F is a morphism between these pre-varieties, then this F scheme is actually a morphisms from this to this of schemes over K. That's one thing you should check. But again, this follows because on an affine cover, all of these maps of K algebras are actually maps of K algebras. They respect how we see K inside them. So this shows this is a well-defined map from the right-hand side to the left-hand side. And now we just show that it's injective and surjective, and we're done, right? And so the first direction is that this F to F scheme is injective. And this is actually not super hard because, well, let's write down these two maps. So somehow we have f from x to y, and then we have f scheme from x scheme to y scheme. If we want to say this is injective, then we need to show this here determines f. So we can reconstruct f like this. And this is actually very simple because we can find injective maps here and here. And these injective maps just take a point A inside X, and then we need to come up with point of X scheme. The points of X scheme were irreducible closed subsets. Well, given this point, you just take the subset given by this. And this is a well-defined map. And you check that this is a commutative diagram. So in other words, this F scheme really sends this subset here to the subset f of a. Okay. And this then becomes a diagram of sets. But then from this, it follows that F scheme determines F. Right? Because you want to know where does F of A go? Well, you can take first this inclusion and then F scheme, and then you land in here. And because this map is injective, there is a unique point in Y mapping to it. And then you define this to be F. So somehow, in a certain sense, the scheme world always knows at least as much as the variety world. So this is one thing. And then we want to show that the surjectivity holds. And so we need to start with a map. So given G from X scheme to Y scheme, map of schemes over K, then, well, what we do is we basically have to mimic this first part here. So choose covers by affine schemes. As above, then all of these affine schemes give you these varieties here. And then these induced maps of affine varieties clue to such a map F from X to Y of these varieties with G equals F scheme. Okay. So we're not giving all of the details here. And Gatman, he basically just leaves all of this as an exercise, but at least I wanted to give the main ideas here. So yes, so this shows that we can see these tree varieties over K inside the schemes over K, and all of the proofs essentially boil down to the same idea that the affine covers of the variety correspond to the give you an cover by affine schemes of the associated scheme. And now the final thing that will motivate us for the rest of the chapter is this allows us to identify pre-varieties as some schemes. And then we need to understand how do we identify then the varieties inside there. And for this, we have to talk a bit about these products and about the diagonal. this will be the last part of the chapter.